Okay, so today let's briefly review what we talked about last time, and then I'm gonna show you how to code the project 5. Yes, project 5, and then move on to chapter 6. Okay, so let's make it clear. Alright, so we need, first of all, map from disk to upper half plane. So this is simply the area inside of the unit circle, and upper half space is just upper part of our plane. And this map, let's call it T, is defined to be U, V goes to 2U squared 1 minus V squared, and 1 minus U squared minus V squared, U squared, 1 minus V squared. So that's X and that's Y. Okay, that's one thing. And then why do we need this? Because we basically want a map on this which satisfies heat equation. But we found the formula that satisfies heat equation on the upper half plane. So that was the following. So when we have this upper half plane, I set this into 4 pieces at x equals to -1, 0, 1 here. And then, let's see, this was C0, C1, C2, C3. So that's the boundary temperature. And our function, the H function, was the following. C3 plus 1 over pi, C2 minus C3, theta, x minus 1y, plus 1 over pi, C1 minus C2, theta xy, and 1 over pi, C0 minus C1, theta x plus 1 y. Okay, so that was my function. So what I want to do is trying to, okay, so let's translate this here. Here is -1, 0, 1. I know C0, C1, C2, C3. So, and also I mentioned that this is -1, this is 0 and -1. And what I mean by that is, this point, the left part of the unit disk maps to this point, x equals to -1. This point maps to the origin, and this point maps to 1. So, in fact, I have to be a little bit, I have to explain a little bit more what happens on here. So this point is actually mapping into the point on the infinity. So here C0, C3 are not connected because they're just different pieces. So these parts are corresponding to all the points on these parts. So this is C0, and this part is C1, and that part is C2, and that part is C3. So you can split the boundary of the circle into 4 pieces, and we can expect that the temperature on that boundary is that. So what I want is found the contour lines inside of the disk which satisfy the boundary temperature here. So I'll give you how to do it. It's not simple because you see, I want this, only the disk, not the entire rectangle surrounding the disk, right? So when I have to go, but when you draw the contour line, you have to set x and y, split it into the several numbers, several points, and this has to be the rectangular region, not the circular region. So you have to use the polar coordinate transformation. So you have to go from the R set of plane to the disk, and then you have to draw the contour plot. So import these two, and let's define that function h. So h is lambda x and y, and okay, so I need to define my C1, C2, C3, C4. So I could use C0, I use C0, okay, so C, let's use it C. So let's see, I'm gonna just put the random value here, -5 and let's say 25. Okay, so and then C3 plus C2 minus C3 divided by pi. And okay, so I need the theta function, but let's just put it theta x minus 1 and let's see. And C1 minus C2 and so on. And then what? C0 minus C1 m pi jump dot pi theta x plus 1 y. Okay. So let me check if it works. So h1, so I need to define theta first. So theta function is a lambda. So here the theta function is ranging from 0 to pi. So it only measures the degree of point at certain point. So here it's a degree of a point at the origin, and this one is shifted by 1, so it's a degree of the point at 1, 0, and so on. So I need the arc cosine. So it's x over x squared plus y squared square root. Let's see if it works. So h 1, 1. Let's print it out. Yeah, I thought something. I was thinking about whether I write this correctly. So let me put it this way. It's just a syntax problem. So let's see. How do I make, instead of one line, I want to make it 2 lines. Let's see. Backslash, okay, this one?
Maybe backslash.
Opposite? Just one backslash? Oh, thank you. Okay, so that works. Now, let's try to make a contour plot on the upper plane, and then let's make it onto the disk. So that's that, and let's make one more code block. So I'm gonna make XX and YY to be the mesh grid on, let's see. So, and I cannot make entire upper plane, so let's make X range from -5 to 5, and then Y range from 0 to 10, and then there is a contour function. So you can use the contour function you implemented on the chapter 3, I think. 3, right? So also you can use the contour function implemented in the matplotlib here. And let's see, XX, YY, and H, XX, and YY here. And let's see the result. So there's something going on here, right? So I want to make it a little bit dense here. So how can I make it dense? So let's see, level. I forgot the argument. So let's see, levels here. Set levels. MP lin space. Let's see, -25. What was the maximum? So I had made my C0 to C3 range from -5 to 25. So that's -5 to 25. Let's see what happens. Okay, so now it's a bit denser here. Let me make it smaller. All right, so you can see, it's different by color, but so what I did is, let's see, on C3, I have to make clear, 0, 10, 0, -5, 25. So 25 is the hardest point, so it's depicted as a yellow color. So it's after 1, so this is 25. You can see that the color is almost the same here. And then from 0 to 1, it's -5, which is the coldest. And then the rest is kind of middle, 0 and 10. So 10 is about green-blue-ish, and 0 is kind of bluish here. Maybe I can I don't have to make it -5 to 5. Let's put it -2 to 2 here. So you can see more color here. So you can see the line, each line is actually of the same color. This line is the contour plot of the heat function. The heat function gives you the temperature at that point. So you're just connecting the point where it has the same temperature, right? So this is how somehow depicting the distribution of the heat. So now let's make it into a contour plot on the disk. So now I have to define my T, lambda, let's see, U comma V maps to array of 2U divided by U square plus 1 minus V square, and minus U square minus V square divided by U square plus 1 minus V square. There's no this thing here. Okay, so that's T. And I want the function, not H, but the composite of H and T, because I want to map from the disk. So let's call it small h. Small h is a lambda that sends UV to first TUV. So then what we get, oh, so I think I should mention this as definition H here. Sorry, so the reason why I'm using definition is the output is different from the input of H. So this one is, first you put that UV into the function T. So this gives you the XY coordinate, XY. And I have to retrieve X and Y. So XY at 0 and XY at 1. So then I put that into the H function to return H, X, Y here. So that's my H. So what I want is drawing the exact disk here. So I need to set up my RT, RR and TT as a mesh grid. So R is from 0 to 1 because that's the radius. And T is from 0 to 2 pi. Okay. So then when I want to draw X and Y, Xn and YY, this is going to be RR times cosine T, NP cosine, and RR NP sine T. Okay, so then my XY is here. So when I draw the contour plot, so I want XX and, so I want, yes, XX and YY and HXX and YY. So here's the picture. Let me draw another plot. So NP cosine, in space, to make a boundary here. NP sine, the Lin space. Okay. Let's make axis equal. Okay. So here's the picture, the contour picture of plot. So you can see this part. So there are 4 quadrants of the unit disk, and each have different boundary temperature. And these ones are what? C3, so 25. And these ones have what? C2, which is -5. And this one is C0, 10, and 0. So you can see, so well, what does this color mean? So color means the temperature, right? And the lines actually means that it's the equitemperature line. So all the points in the same line are having the same temperature. So you can see that each line has the same color. So you can see that this line is of the same color, right? It's not changing. Right. So I'll put the code up in here. So any questions? So this basically is the end of the chapter 5 and project 5. So if you're doing project 5, you have to you want to do something differently from this point. So there are many things you can change a little bit. So you can change your boundary cut into different places. So then we'll give you a different cut of the boundary of the disk. And also you can make into 5 pieces or 6 pieces. If you want, you can change the shape of the disk. As I said, every mathematical concept that we are learning these days are very important, but especially if you're trying to do some research or pursuing your career in AI, you have to understand what we're going to talk about today and the next day. Because, so basically, what we're going to do is discuss about the chain rule and the gradient descent, which is the most primitive form of machine learning. All right, so let's talk about the chain rule first. So I'm going to write down chain rules, several chain rules in different forms. So first, I think we discussed a long time ago, what is the chain rule for single variable function? So if it's maps from R to R, and also there is G, R to R, and let's say these functions are differentiable functions, then the chain rule says if I take the derivative of composite function, it's same as what? The product of derivative of 2 functions, right? That's a chain rule for a single variable function. And the reason why this makes sense is, I think I mentioned this in a 2 different ways. You can either look at the graph, or you can think about the meaning of the derivative as the velocity for the rate of change of velocities. And let's think about different types. So we have change the function R2 to R. So it's a 2 variable function. It takes 2 variable x and y, and then the number maps to a number, let's say z, through the function f. And then you can have another function c that maps r to r squared. So what does this mean? So there's a reason why I mentioned it c instead of g. So it maps a point in R, which means that you can think of this as a time. Okay, so it's a time. And then this maps into some point, x, y. So this x and y changes according to time. So you can think that this c is a curve, a parametric curve. And this function basically is mapping of x, y into z. So what happens when you take a composition f and c? So what is the type of this function? So first, it feeds with a time variable because it must go to the function c first. So c only takes the time variable function value t, and then it gives x, y, and then it feeds the function f, and then it gives the value, which is z, right? So this is z. So here, I'm thinking about the value of function to be a z coordinate in x, y, z space, okay? So you can see that this composite is just a single variable function that takes the time t and the value of z. What I want is take the derivative of this function. So here, f composite c derivative. So when I say derivative, right now I'm not talking about the differential or I'm not distinguishing the differential and derivative. I'm just picking as the same thing, because you can always just plug in specific number to the variable t or x or y to get the value. So just if you want, you can think t as a number, or if you don't want, then just take it as variables. And that is same as the prime t. And what is this equal to? So think about the meaning first. So I have a function, or graph of a function, and I have a domain of a function f to be an xy plane, entire xy plane, and there are a curve that is moving inside of xy plane. And let's see, here is the graph that equals to fx, y. What I'm doing here is, as the point is moving along the curve, I want to see how the height, the z value of the point on the surface of the graph of a function f is changing. So the rate of change of height is the z prime. So how do you measure that? Think about how you measure the height, rate of change of height. So at a certain point, you're moving in certain direction, right? That's c prime t, right? So at that moment, you want to see how fast the height is changing. So there is a concept that exactly measures that rate of change. What do you think that is? So at the point ct, the point is moving in the direction and speed of c prime t, and I want to see how the height is changing. So you can cut, let's say, this, if you take the line, straight line, parallel to this vector, you can cut the entire surface, right? And you get the section. So if you want the rate of change of height, it's same as looking at this surface, the section including the below here, and then put it the straight here, let's say is. So this is the not x or not y axis, it's some kind of direction that parallel to x prime t direction. And this is where ct is, and this axis is actually same as z axis. And you want to see the slope at right here, right? Maybe not right here. So sorry, the picture is kind of leading there. So since I had point c prime here, so ct somehow ct is here. So you want to see the rate of change of the height. That means you want to see the slope. So this slope is the rate of change of the height. So height is actually the zt, right? At ct. How do you take the slope? We learned about this, so I'm just making a quick quiz. What is the concept that gives you that slope? What is it?
I don't actually remember the name of it, but I think it was about the nebula.
Nabla. Okay, so similar. Nabla is we introduced nabla only when we introduced the Laplacian. But also I don't remember whether I mentioned this before. But do you remember directional derivative? What is the directional derivative? You guys remember what directional derivative is? Maybe did I mention this or not? I should have mentioned this when I introduced the partial derivative. Maybe not. Okay, so let's review again. So see if you remember this. So if you have a function, and at certain point, and you have a vector v inside your xy plane, and the directional derivative in the direction of v of function at x0, y0. So we use all three information here, is the limit of t goes to 0, here f x 0 plus at, y0 plus bt, minus f x 0, y0. Okay. Make sense? Did I introduce it or not? I think I introduced. Okay, anyway, so this is the directional derivative. So what is that measures? So it measures the difference of value of function with t. So what is t? So t appears in the inside of this function as a point. So it's making a change from x0, y0 to the direction of a and b by t. So t is kind of the unit of the vector. I mean the length of a vector that you're changing into that direction. And then you're taking a point x0, y0, and then moving this point away from that in direction of v and the speed of v by amount of t. So if t equals 1, then you're actually changing that v amount. When t equals to 0.1, then you just take the 1/10 of this vector v and then make a change. So that's your point. But you're taking t equals to 0. So you're not making a large change. You're making an infinitesimal change in direction and the speed of that vector. But you also want to see how the ratio is converging to. So you want to see the infinitesimal rate of change of the value of function in direction of v. So usually we take v to be the unit vector, which means the length equals to 1. So you're asking, what if I move from that point in the direction of v infinitesimally, then how much my height or the value of function changes? That's my question. And that is exactly what we are looking for here. I'm here at CT. I'm moving in infinitesimally by c prime t, and I want to see how much my value of function is changing, how fast my value of function is changing. So this is same as the c prime t f ct. I want to see how much change in the direction, how much is the directional derivative of this function. So how do you find that? How do you find that? So you can use the x direction and y direction. So think about it this way. If I move in the direction of speed of 1 in a certain time and see the rate of change of my function, and then, let's see, if I take the same vector and I want to move twice as fast as the same direction at the same point, the rate of change will be twice, right? If I change the speed by twice, I may increase the speed by 2, then I've changed the rate of change by twice too. So it really doesn't matter whether I take the c prime t to be a unit vector or not, because I just take the vector direction and then just take the size of the vector to be multiplied to the directional derivative. And also what I can do is I can split up this c prime t into x vector and y vector, x direction and y direction. Let's see here. So here, it's moving that way. So we have x vector and y vector, so cx and cy here. And then I can see how much the function changes if I move into cx direction, which is parallel to x-axis, and also cy direction. And then the total amount of change will be approximately same as the rate of change result by cx direction movement and cy direction movement. So this is actually given by, so I'll have to make a little bit of notation here. Let's say c prime t equals to ab. So then it's a times f of x, b times f of y. So I'm trying to show you I'm trying to convince you why the chain rule makes sense. So I'm just giving you the kind of a derivation of a chain rule. So I'm not stating the final result. I'm just giving you the idea how to derive it. So first of all, what is A and B? So A and B are x coordinate and y coordinate of c prime t. So ct is the position, c prime t is the velocity. So how do you get the velocity coordinates? You first take the derivative of coordinate function, because coordinate is a position. If you take the take a derivative of position, you get the velocity. So AB is the velocity functions of x position and y position. So in here, you're multiplying each coordinates of the vector c prime with f of x and f of y. So f of x is a very special directional derivative, which means that you're taking a measure of the ratio when you move your x coordinate only and fixing the y, and similar to fy. So you want to move your x coordinates in a unit vector, a unit speed, but the actual vector has no unit speed in x position, right? So you have to kind of scale this, the directional derivative, the scaled amount of the rate of change result from the unit speed change by a, because that's how much you actually change your x points, x coordinates, and same for y. So we have you have a rate of change of the function when you move your y coordinate in the unit speed, but the actual speed of movement of y coordinate is not unit, it's not 1, so it's actually b, so you have to scale it by b. So that's your slope, and that's your rate of change. That's your directional derivative. So what can you say about this is if you take the directional derivative, here. So again, this is the rate of change of your value of function, or z, or the rate of change of height, whatever, is equals to a times fx plus b times fy. So let's, instead of using a, b, let's make it fancier. So we have, this is x coordinate and y coordinate. A and b are the speed of this movement of points. So a is x prime, okay? A is the rate of change of x, the speed of x, so therefore it's x prime. And actual rate of change of function, f of x. So here f of x is a function of x and y. So here, where does xy come from? Xy comes from the coordinate of the function c, so it's ct here. Okay, so that's a f of x. And then b f of y, b is the speed of y, y prime t. And then f of y is the partial derivative, but x and y is coming from ct, so ct here. So instead of using xt, yt, I'm using ct here because that's the same thing. That's the ct. So that's the chain rule for this particular case. Okay. So now I want to go a little bit further, because I want to show you that the chain rule for a single variable function is actually have the same format in this case. So this is just a number, but let's think about this as, let me write it here. Matrix multiplication. So let's look at the matrix multiplication of two derivatives. So f c prime t is with that t, whatever, but that prime t, okay? So this was the single variable function. F composite c is just a single variable function, zt, right? And you take the derivative, it's zt. But let's look at zt as a 1-by-1 matrix, because it's a number. Every number can be considered as a 1-by-1 matrix. So how do you obtain this 1-by-1 matrix? And I know that this is equals to that, x prime, fx, y prime, fy. And you can see that this is actually x prime, y prime, sorry, the opposite here, fx, fy primes, x prime, y prime. So if you multiply fx, x prime, you get this term, and fy times y prime, you get this term. 1/2 times 2/1, right? What is this 1/2 matrix? This 1/2 matrix is actually the derivative of f. F is a function from R2 to R. Remember the definition of the derivative of multivariable function. The multivariable function derivative is always matrix. And the size of a matrix is determined by the number of their variables of inputs and outputs. So this thing is the derivative of f. Usually we call it f prime, also del prime or d prime. And what is this part? 2/1 matrix. This 2/1 matrix is the derivative of c, this parametric function. So it's from R to R squared. So it's a 2/1 matrix. The derivative of c is 2/1 matrix. And it has a two function that determines the coordinate of the output variable, the x and y. So this is the derivative of x and this is the derivative of y. Because there's only one variable, it's not partial derivative. It's just a normal derivative. So that's dc. So just a side note, you can write this f to be f prime, df to be f prime. You can also write dc to be c prime too. But then you can see that the chain rule for a single variable function is same formula as the chain rule of these two functions among the two multivariable functions. So the derivative of composites are becoming a multiple or a product of two derivatives. That's the meaning of the chain rule. So let me show you the example here. So let's see, f of xy to be xy. And ct to be cosine t, sine t. Okay. So what we're going to compute is the equation, left-hand side and the right-hand side of the equation. So let's first compute the left-hand side of the equation of the chain rule. So first, let's compose C and F. So let's call it, let's say Z. So Z is what? You're plugging X by cosine T, Y by sine T. So you get F of cosine T sine T, right? So this is, the value is X times Y, so cosine times sine T. So that's your Z. And now let's take the derivative. F composite C prime T is you're taking derivative of this. Well, you can use a chain rule or a product rule, or you can make it into 1/2 sine 2t using the sine rule and take the derivative of this. Let's use this. So then I get cosine 2t, right? So on the left-hand side of this chain rule, I got cosine 2t, and now let's compute the right-hand side. So first I need to compute df, the derivative of f. So f is here. What's the derivative? df equals to 1/2 matrix. First, there's only one function. You first take the derivative, partial derivative of the function by x, y, and then by y. So you get, that's your df. And what's dc? So you get c here, it's 2/1 matrix. Take a derivative of first and second coordinate functions. So we have 1, 2. So minus sine t and cosine t. And the right-hand side says it's df times dc. So let's take a times, not composite, times dc. So it's yx times minus sine t cosine t, right? So we get minus y sine t plus x cosine t. Okay, so I got this one, and I had this one. Why are the same thing? Because I have x and y. There's no x or y here. What's wrong here? What's going on? What is x and what is y? Are they independent to x and independent to t? No, x and y are not independent variable of t, because x and y are determined by these formula. These are x and y, okay? These are x and y. So you cannot think x and y as a separate variable than t. It's just some formula in terms of t. So let's use that. That's sine t. Y is a sine t. So sine t times sine t. And x is a cosine t. So it's a cosine t, cosine t. So it's a cosine squared minus sine squared. What is it? Cosine 2t. Now we get the same thing, right? So whenever you use the chain rule, don't forget your functions are kind of connected together, connected through their domain and codomain. So these two functions, I mean, if you think of these functions separately, then there are two different functions. But we are trying to see that the codomain of the first function is the domain of the second function. So they are related between these, the variables are related by their formulas here. So you can see that the chain rule actually works. So I'll give you a different meaning, another way of thinking about the chain rule. So again, let me rewrite the formula above here and then give a picture. dfc equals to df times dc. So on the left-hand side, we took the derivative of the composite. Since it was a single variable function, so I just took the prime, but you can also write it as a d notation. Or you can also write everything into prime notation. It doesn't matter. The meaning is different, and meaning is important. The notation is not really important. So we have, see, you can write this way. So anyway, what's the meaning of this? Again, so think about this way. So we have R maps by R2 by C, and then maps to R again. So here, this was the t-axis, and this was x-y-axis, and this was z-axis. Okay. Well, you can kind of put it into together three-dimensional picture, but I like this one. But what happens here is I'm moving my point T along my t-axis. Okay, so I was moving my t along my t-axis, and then at t I had some point in xy plane, And because I changed my t, my point is changing too. But infinitesimally, I'm changing my point in c prime t direction because of that. And also because I changed my coordinate infinitesimally in this direction, I also changed my z infinitesimally in z axis. So all I want is all I want is how much my z coordinate is changed, how fast my z coordinate is changed. There are two ways of calculating this. Either you can take these functions, composite of these two, c and f, and then direct relationship between t and z, and then see the rate of change of z according to t. Or you can see the chain reaction of this. So because t is changed, ct is changed because of the mapping of c. And then because ct is changed, you can see the change of z by the action of f. So chain rule only says that it doesn't matter whether you see the rate of change of z by the chain reaction of these two composite functions, or just see the direct relationship between the first coordinate and the last coordinate. And this idea is everything. This idea applies to the most general form of the chain rule. So I'll give you the most general form. You don't have to remember all the details if you just understand this. So let's say f is the function from Rn to Rm, and g is a function from Rm to Rl. So these are the most general form of multivariable functions. And the codomain of f and domain of g is the same thing, so I can composite these two functions like this. The first f and then g, right? So this is mapped from Rn to Rl. It makes sense? The f must feed with our n-dimensional points, and then feed them into the result is feed into the function g, and then g gives l-dimensional points. So it's l to l, n to l function. So now, if I want to take the derivative of this composite function, the chain rule says this is equal to dg times df. So again, let me, once for the last time, make an emphasis that this is a composite or composition of two functions, and this is matrix multiplication. Okay? This is your chain rule. Let me write that chain rule, the formula, into different notation. So, chain rule and formula. So first, if f and ct, and let's use this formula. So let's say if f is so if f is p to x t y t and g x y is z, then think about formula that we just, this is the same situation we talked about just now, and think about what the formula should be. So then dz dt equals to dx dt del f, so del z del z del x, here, plus dy dt del z del y. Think about it again. So here, so I'm writing the equation, the same equation in a different form. So on the left-hand side, it was zt, right? So g composite f, which is this, so it's about g composite f. You plug in x comma y here, so basically it's a function of t. So that is a function of t when you composite these two functions. So on the left-hand side, you're taking a derivative of that composite function, which is single variable function. So it's not partial derivative. It's just a single derivative, single variable derivative. And on the right-hand side, you're taking matrix multiplication. So what is DG? So it's the derivative of that here. DG is 1/2 matrix whose coordinates is del Z del X, del Z del Y, right? And what is DF? DF is this, the derivative of this function, which is parametric curve, which I wrote it as C. And it's the 1/2 matrix, X prime and Y prime. So when you take the X prime and Y prime, you're taking a derivative of single variable function, which is dx dt, dy dt. So same equation. So let's do another thing here. How about this one? So we have f x comma y. Let's see, x comma y as z, and then g as z. Oh, let me put t here. So let's put t here. T, and then gt is somehow x, ut, and vt. Let's plug that in here. So let's first see whether it makes sense. F composite g. So F composite g means x comma y is mapped to t, and then t maps to uv. Okay, so it's a map from xy to uv. So 2 to 2 functions. It maps two-dimensional point in xy plane into two-dimensional point in uv plane. So F composite g is what? The derivative of x to u. So ux, uy, vx, vy, right? Because this function is mapping x comma y to u comma v. Whenever you have this function, the derivative 2x2 matrix with coordinate is partial derivative. And now let's think about the derivative separately, dg and df. What is dg? So it's 1 to 2 function. So it's a 2x1 matrix, right? What is it? U prime. Because there was only one derivative, so there's one variable. So only derivative is the just normal derivative, u prime and v prime. That's your dg. Right? And what is df? df is now 1/2 matrix because only I have t. So now t is determined by two variables. So there are partial derivative, tx and ty. So the chain rule here says that these 2x2 matrix and the multiple of these two matrices are the same thing. So let's complete the matrix multiplication here. So what is it? U prime tx, or first row, first column, and first row, second column, u prime ty, and v prime tx, v prime ty. So what does it say? So if you want ux, this is the same thing as this. So ux means it's a partial derivative of u in terms of x, and that is equal to du dt times del t del x. And same thing for other parts. Like this one, we have del u del y equals to du dt times del t del y, and same for this. So let's look at this one equation. So there are 4 equations, and see whether it makes sense. And see that you want to take the partial derivative of u in terms of x, and which means that you want to see how the value of u is changing according to change x. But u is determined by one variable, which is t, right? You want to see how much the t is changing. But then t is also determined by x and y. But here you're changing x only. So when you change your x, you can see how t is changing. And because t is changing, you can see how much u is changing. So it all makes sense. All things make sense. And also here, if you want to see how much u changing according to y, first, when you look at u, it only determined by the rate of change of t, but the t is determined by the change of y, so therefore you can just multiply these two. So it's a chain reaction. So rate of change of u is determined by the rate of change of t, and the rate of change of t in this case, because y is the only thing that changes, is determined by the change of y. So this also makes sense, and the rest of the thing we can stay similar to same. So let's see, let's look at another one. So just just to make sure that you have all the possible way of writing the chain rule. The third case, let's think about this case, is when you have f to be u comma v to x comma y. So it's kind of changing the coordinate, like a polar coordinate system. So, and also g is mapping your x comma y into some variable z. So what is DGF? So you see uv is sending to z here when you take the composite. xy is just the intermediate variables, right? So you're taking a derivative of 2 to 1 function in this case, so therefore it's 1 by 2 matrix, 1 by 2. The final variable, final function is z, but this z has to be considered as the z of u and v. So therefore it's z del z del u, first coordinate, and the second coordinate is del z del v. Okay? And now the chain rule says it's same as dg df. What is dg? So dg is 1 by 2 matrix, zx, zy. Right? And what is del f? df is 2 by 2 matrix, so it's row and columns determined by this. So each row has the same coordinate function. So the first row is about x, and the first column is now take a partial derivative in terms of u, del x, del v, and del y, del u, del y, del v. So sorry for not writing in the same line, but you're multiplying 1 by 2 matrix with 2 by 2 matrix. So now the chain rule says these has to be the same. The 1 by 2 obtained by multiplying these two matrices has to be the same thing, which means that entry-wise that has to be the same. So look at the first entry here, del z del u. How do you obtain the first row, first column entry on this matrix multiplication? You take first row, first column, right? This one multiplied with this one and this one, side by side. You have del z del x, del u, plus, no, second one, del z, del y, del u. So now you check the first column entry here. Now let's look at the second column entry. Del z, del v equals to this one multiply this one. So del z, del x, del v, and del y, del z, del y, del v. So these two equations is the chain rule of this case. Now let's look at this carefully. So again, you only need to remember this one, but sometimes it's better to look at the specific notation of partial derivative to understand what's going on inside of the chain rule. So on the first equation, on the left-hand side, what you want to see is the rate of change of z according to u. So you're only changing u. You're changing the u only in UV plane. But you want to see, after changing through the xy plane, you want to see how the z is changing. Right? That's all we need to know on the left-hand side. But on the right-hand side, what it says is the u is changing x and y. Right? According to change of u, you have change of x. And also, when you change u, the y is affected. So there is change of y. So you cannot just think about the change of z according to the x or y separately. I mean, only. So you have to combine this action of combine the results of change of z according to x and y. So there we have change of z according to x, and this change is affected by the change of x according to u. And then you have to add another effect of change of z according to the y here. The same thing happens here. So you want to see the change of z according to v, you have to see the change reaction through x and y. So easy way to remember this formula is that you're kind of canceling out this x here and y here. So all you left is del z del u here. But you cannot just ignore one part because they are both affecting the rate of change. And same for here, del x, del y cancel out, and then you get this del z, del v left only, right? So once you have this formula, I think that's everything. So this is the most general form. The rest part is that we can just simply change the notation of x and y's here. That makes sense? I want you to take some time to think about this more carefully, and then if you don't understand, or maybe I can give you some example and then take a question here. So we have three kind of formula. So let's work on the last one. So here is the question. Here's some example. So let's see, f u v is u v comma u squared plus v squared, and g x y let's see, cosine xy. I'm just making a random formula. So I want to first check whether these equations are satisfied or chain rule satisfied. So this is my z, okay? And since these are connected, so whenever you want to use the chain rule, it means that your intermediate variables are connected to each other. So these are formulas of x and y in terms of u and v. So therefore, even though that is a function of x and y, in principle, it's actually the function of u and v. So if I write down that in terms of u and v, I simply substitute the formulas of x and y here. So we get cosine uv u squared plus v squared inside, right? So then I can just simply take the partial derivative of this function, because now it's a function of u and v. And this becomes minus sine uv u squared v squared, and times the derivative of inside, which is v u squared plus v squared plus 2u squared v. Right? That's one way you can compute this, and the chain rules gives you another way on the right hand side here by taking the partial derivative of these functions. So first, let's take partial derivative of that by x. So here it means that we want to see the z as a function of x and y, right? Like here, as it is. So we have minus sine xy times y, right? So just taking the partial derivative here, and then take the partial derivative of x by u, right here. So x is also the function of u and v right here. When you take the partial derivative, it's just v. And let's take another one. So y is del z del y equals to this. So we have, I don't know about this here. So sine minus sine x y times x, and del y del u, y is y squared plus v squared, so it's 2u. So now let's put that in here, this formula. So what is it? Minus sine xy times y times xu, which is v, plus minus sine xy x times yu, 2u. So that's the right hand side. So are they the same thing? So I want this to be equal to this. Are they the same thing? Well, again, you shouldn't think the u, x, and y are different or independent from u and v, because they are related. So related by this equation. So if you plug in x and y using this formula, you get this here, right here, right? And also same thing goes here, sine x and y. So all you have to do is whether yv plus x 2u equals to this. Well, I think it's the same thing. Y is here, x is uv times 2u gives you this, right? You can see easily why this is the same thing. Okay? Questions? So think about this, and you have to have questions. So, so I've been feeling that these days the computation is all. I mean, the skill of computation is less important, less and less important, because you can get a computational answer easily by using the computer or AI, whatever. But you have to understand the meaning of what's going on. So let me give you another meaning of this. So this is just a formula. And think about meaning again. So I think I already gave the meaning, but this is the one that I gave you the examples of the specific case. I mentioned the meaning, but let's also give a meaning in these settings here. So what is going on when you take a composition? So we have three different spaces. So this is Rn space, this is Rm space, this is Rl space. So I'm not saying that these spaces are two-dimensional, even because I made it into two-dimensional. I'm just saying that this is a symbolic picture of this higher dimensional space. So when I say higher dimensional, I'm not saying three-dimensional or four-dimensional. I'm saying 10,000 dimensional, 1 million dimensional, because that's what's happening in your AI machine. When you ask them question in your AI machine without paying anything, they're actually doing lots of computation, right? So in that computation, they're not using 3, 4, 5 variables. They're taking trillions of variables. Search how many variables of this ChatGPT uses these days. More than trillions. So anyway, so this is function f, and this is function g. And what's going on in the chain rule is I have a point on three different spaces. So let's say this is P, and this is Q, and this is R. So P is mapped to Q, and Q is mapped to R. I don't want to see the actual point. I want to see how the rate of change of each point is changing the resulting points. So if I change P by the direction of V, the Q is changing in certain direction, so it's moving in certain direction by W. And because Q is changing into W, in direction of W, the resulting point R is changing also in some direction U. So there are two ways. So final thing that I want to see is the change of R. That's the goal. But there are two ways of looking at this, either in a chain reaction like this or in a direct relation. So in a direct relation, we just see that P is mapped to R, and when P is changing to V, I want to see how U is changing. So in that circumstance, what happens is I have D of F composite G, and then I map this vector V through this matrix or derivative, I get U. That's what's happening in this direct relationship. So again, I think you have to remember what the meaning of the derivative is. Derivative is a mapping of a change of inputs to the change of output. This is your change of input. This is your change of output. This is the derivative of the direct relationship between the first and the last function, last space. But chain rule says you don't have to do this. You can split them up into several stages, right? So sometimes your relationship between these two spaces could be separated into several stages. So I'm not saying you always have to start with these separate stages. Let's say you have this map, original map, and somehow you figured out that you can make it into a composition of smaller functions like f and g. And the chain rule says, okay, so if you look at the f, then it maps v to w, and then w is now mapped to u by the g. So therefore, what happens? You can plug w part here, and then this w becomes dfg, right? fg, dfv, and then that must be the u, right? So this equation is when you look at the direct relationship. This equation is when you look at the chain reaction. So v and u is just symbolic notation of change of input and change of output. You can delete it every time, right? So whatever your u and v is, it has to be the same, even when you look at this way or that way. So therefore, this matrix multiplying on the left side of the vector must be the same thing. So this one has to be the same as this one. So that's the meaning of the chain rule. So again, going back to the AI story, that you have a trillion of variables to determine what's going to be the right answer to your questions. So AI is not examining all the trillion variables at once. So they are splitting it into several stages, small stages, so that it makes boost on the computational speed. That's why you couldn't get an answer right away. How can you get an answer so complicated? So therefore, the chain rule, why chain rule here? That's why we're looking at the chain rule here. So again, last question. Any questions before we move on to the next part? Because now we want to move on to the optimization problem. The chain rule used for optimization. No? No questions? Okay, so I'm going to give you an outline and probably cover only a small part of optimization today. So I'm not talking about the entire optimization in the world. So I'm just giving you something that we can talk about using the calculus idea. So the first optimization is using the Hessian, so it's Hessian's method. And also the second is Lagrange method. Not Lagrange. Lagrange multiplier. And the third one, now once we have 1 and 2, actually we don't want A, but the 1 is not directly related to the second and third, but it's always been a subject in the calculus, so I have to cover it. So third one is about gradient descent. And the fourth one I want to cover is the neural network. Now it gets actually AI thing and image processing. So along the way I introduced the neural network. I'm going to talk about the image processing, which is the project 6. So let's talk about Hessian first. So in fact, Hessian, the first topic of the optimization is not related directly to the chain rule, but I had to talk about the chain rule first because I want to help gather all the optimization methods into one. So what is the Hessian? What is the method of optimization within Hessian? So what we want is, again, the following theorem about the Taylor polynomial. Taylor polynomial theorem. Well, maybe let's make a definition. So theorem, if I have to state the theorem, it gets really complicated. So let's just write it as a definition. So let's say we are given with a 2-variable function f of x, y, and which is differentiable up to third order. So which means that there are second order partial differentials, and you can take one more partial differential of the second order partial differentials. So you can just say that there has a second order partial differential of every kind. So then the following polynomial is called the Taylor polynomial. Of the second degree. So P x comma y is fx at x0 y0 plus fx x0 y0 x minus x0 plus y x0 y0 y minus y0, and then 1/2 fx x0 y0 minus x0 squared 2 fy x0 y0 x minus 0 y minus y0 plus y x0 y0 y minus y0 squared. That's a long one, but the first part is just linear approximation we talk about when we talk about differentiability of a function. So we only add the second part, which is the quadratic equation. You can see it's quadratic because we have a square terms here, here, and here. And all the coefficients are just numbers. You're taking a partial differential, not partial derivative. It's just a coefficient number. And we call this Taylor polynomial. And what does that mean? So when you take the linear approximation, the first part, it is given by the following principle. So the polynomial p has the same partial differential up to second degree with the function f. So you can see that when you plug in x0, y0 in the polynomial, you get the same value of function. So which means that original function is the zeroth order partial derivative, so you get the same value of the zeroth order partial derivative. So and then, if you take the second order partial derivative, first order partial derivative, what is it? When you take the partial derivative of this polynomial with the x here, and then plug in x0 and y0, all the parts here will disappear. I mean, this whole thing disappears here. And then only thing that survives is this coefficient right here. So this is same as f of x. And same for f of y. So if you take the partial derivative in terms of y, you get the value of partial derivative at x0, y0 with terms of y. And since this is a second order partial derivative and second degree, what happens even more is when you take the partial derivative twice of this polynomial, the only thing that survives is this thing, right? Everything else is just disappears as to zero. And then when you take the partial derivative, because you have a square, so the 2 comes out and then cancel with this 1 over 2. So exactly the partial derivative, second order partial derivative in terms of x and x is x here, right? So all partial derivative up to second order of p is equal to f of x, partial derivative of f of x. Okay? So you can say that this function p kind of resembles the value of f. So which means that p, the value of p, is almost same as f near x0, y0. So the argument, the last argument, is actually the theorem of the Taylor theorem. So we talked about the Taylor theorem for single variable function, which means that if you increase the degree of polynomial, Taylor polynomial, then the error goes to 0 in some cases. But it happens for the multivariable function. So if you have this, I mean, not only for the second degree polynomial, you can get nth degree polynomial, although the formula gets even much more complicated than this. If your point is sufficiently near these points and you have a certain condition that the partial derivative doesn't go infinity, then the value of function of p is almost same as value function of f. So that's the point of why we're using the Taylor polynomial to think about the shape of a function. So this part, linear approximation, again, is used when we talk about the differentiability of function. The differentiability is actually equal to the function, the graph of function is kind of same as a flat surface if you enlarge and enlarge sufficiently enough. But this polynomial gives you a little bit detail about the shape of a function or graph of the function at that point in a quadratic sense, which means that it could be flat, but what if we want to see in which direction the surface is concave? So is it concave up or concave down, which means that it's a kind of a minimum or maximum, or it's a saddle. So that's the point. So here is the classification. So theorem. So let's say D is fxx fyy minus fxy squared. So first of all, if f of x, x0, y0, and f of y, x0, y0 are both 0, then the following classification. Oh, so here is a case. So you look at f of x or d and classification of x0, y0. So basically what we want to see is the value, how the value of function is, what kind of value of function that is at the point x0, y0. So if f xx, so what I have to be careful about is it's not the formula, it's about the value at x0, y0. If it's less than 0 and it's positive, or maybe I should just write a symbol minus sign, plus sign here, then it's a maximum, local maximum. Point. And if it's positive and positive, it's local minimum. And it doesn't matter what that is. If it's negative, then it's saddle. So I'll give you the picture of these three cases. So first of all, you have to be careful that the condition of this theorem is that you have fx and fy to be 0 at that point. What does that mean? Your rate of change is 0 in both directions, x and y direction, which means that your rate of change is there's no change in x or y direction. So in other words, if you look at the linear approximation function here, which is the tangent plane, it's flat, and of course it's flat. It's parallel to xy plane, right? So it's kind of a xy plane raised above the surface to tangent to the graphical surface. So here's the picture. So local minimum, which one is first? Maximum. So if you enlarge the picture at that point, in that case, your point is at the tip. So if you look at the tip, x0, y0 is here. And the tangent plane at that point of the graph is flat, parallel flat, right? And the other points nearby that point have the value less than the value at that point. So that's local maximum. It has to be local maximum. So how about local minimum? So it's like this. So this is x0, y0, and the tangent plane is also parallel flat. But also all the points nearby x0, y0 has the value bigger than this point. So that's a local minimum. And what's the saddle? Saddle point looks like this. Have you ever eaten a Pringles? It's a Pringles. So here is the saddle, x0, y0. Okay. So what does that mean? Okay, so if you go along this line, the value of that point, value at that point along this line has a larger value than the point here. And if you go along this line, then the value of function has actually smaller than this point. So you cannot say this is always minimum or always maximum. So in technical terms, if the point is not local maximum nor local minimum, it's always saddle. So saddle is not always this form. It could have a more complicated picture than this one, but this is the simplest saddle I can give. So this is the saddle. Okay. So I'm not going to go detail into this proof theorem today, but probably tomorrow. But what we are doing here is find the extremum of the point, of the function. So either local maximum or local minimum. Among those two, there should be global maximum or global minimum. Okay? So if you are provided that your function is defined in the entire function, entire plane, right? So some have a higher point, some have a lower point. You want to find which is the maximum, the highest or lowest. Then first thing you have to search for is locally in the neighbors, which is the highest, which is the lowest. Then once you have these candidates, take the value of function and then take the maximum, take the highest as a global maximum and global minimum too. And also in the saddle, you can see what is going on in that point, at that point. Because if you just draw the function, you may not know what's going on because the picture is so big, then the small minor change of the function doesn't depict it on the graph. So you might want to find the exact point where the saddle or these kind of thing going on. And then if you have convinced that this point is a saddle point, then you can enlarge the picture at that point and then see the bigger magnifying picture, what is going on near that point. So that's way you can that way you can have a better visualization of the function, right? Instead of just globally drawing all the points randomly and then hoping to search for the local maximum or local minimum. So maybe tomorrow I'll give you some coding example to apply this theorem, and then also we're going to talk about other type of optimization.